Right. In this question, we are given that there's a block of mass and that is attached to an ideal spring whose other end is fixed to a wall. The block is displaced to a distance of x naught to the left of the spring's equilibrium position as shown over here. So this is the equilibrium and is displaced to the left by a distance of x naught and is then released from rest and oscillates with negligible friction around the horizontal surface. When the block is oscillating, it has a maximum speed of V max over here, right? The energy bar charts in figure 2, there you go, we have figure 2, represents the spring potential energy US of the block spring system, and the kinetic energy of the block as the block passes through the positions negative x naught, 0, and positive x naught while the block oscillates. Now the bar chart at x equal to minus x naught, the bar chart at x equal to minus x naught is complete. Okay, this is complete for us, this one. Draw a shaded rectangles to complete the energy bar charts in figure 2 for the position these two. Positive energy values are denoted above the 0 line and negative are below. Shaded region should start at the dashed line representing the 0 energy, represent any energy that is equal to 0 with a distinct line on the 0 line, and relative height, relative height as well. So I think this should be okay for us because we know that since there is no loss of energy, and when it comes to the equilibrium, the spring is going to come at its natural length, and at the natural length, the spring won't really have any potential energy, right? So for us, this portion will just become 0 as soon as x is 0. So this is just a 0 over here, and the entire energy is going to convert into the kinetic energy of the block. So we're just going to draw a rectangle that is at the same height as the potential energy, that is at x equal to minus x naught. So this should be our answer. And when it is at x equal to plus x naught, then eventually exact same thing is going to happen. It won't really go negative because this potential energy's formula is k over 2 x naught square. So even if x naught is negative, it doesn't really make any difference because that's a square. So once again, kinetic is going to become 0 and the entire energy will be converted into a potential, spring potential over here. So that's what we have with the same height. All right, excellent. What is the next question for us? Let me just clear this up. All right, looks a little more decent. Um, Figure 3 shows the position. Let me zoom in. Figure 3 shows the position of the blocks. Where's figure 3, by the way? Here. So it shows the position of the block as a function of time. And figure 4 shows the force exerted by the spring as a function of time. All right, cool. What is the question, by the way? All right, there you go. Using figures 3 and 4, determine an expression for the spring constant of the spring. What other information do I have? I see, I have Vmax, and you know what? I'm going to borrow this figure from here so that I don't have to go here and there. All right, let's keep it here. And let's try to use this information now. All right, I know that whenever the force is maximum at x equal to 0, don't you think this force is definitely the maximum one, right? And we know that at this point, so isn't that just the maximum force that is acting over here? We know that F max is equal to K times X max. And F max is just F max, and X max is X naught, right? It's given right here, X naught. So the value of K will be F max over X naught. That is K. All right. Now starting with an equation for the period of the mass of a spring, derive an expression for the mass of the block, IC. Express your answer in terms of these things. Begin your derivation by writing a fundamental physics principle or an equation for the reference book. So I know that the time period for a spring mass system is given by 2 pi square root m over k. I need to find the mass in terms of all this. So I'm going to square both the sides because I need to get this away from the radical. Or maybe I can divide by 2 pi both the sides first. So that looks like this. Then I can square both the sides. So t square over 2 pi square is 4 pi square, and square of m over k root is just m over k because radical will disappear. I'm going to multiply k both the sides, so it will be t square k over 4 pi square is equal to m. However, in our answer, they do not need capital T and they don't need k as well. So that's fine. We can eliminate because from this curve, don't you think I have the value of the time period? It is 2t naught because that is eventually the time taken for one cycle, right? So I'm going to replace this capital T with 2t naught and 4 pi square as it is, and this is also square, and k we already found. It is f max over x naught. That is the value of small m. So small m comes out as 2t naught square is 4t naught square, 4 pi square, f naught over x naught. These two are gone. So finally the answer is f naught t square over x naught pi square, which is absolutely only in terms of these attributes that they mentioned over here. So that should be our answer. In this question, in part C, they are asking us to graph the velocity time curve over here. All right. The period is not going to change. The period is still 2t naught, what was here, what we saw earlier, right? Okay, so it starts at x equal to 0. This is the point when x is 0. So this should again be the point, sorry, it started at x equal to minus x naught, sorry. So this should again be the point where it is at minus x naught. This should again be the point when it is at minus x naught. So don't you think it makes sense over here? This is 0 and this is x naught. So after half time period, it should come here because after another half, it will again come back. So half time period is over here. So at this point, it should be at x naught. X naught. So this should again be at x naught. So in between this, it should pass the equilibrium point because equilibrium point is the point where the velocity is maximum. So it will hit the maxima over here. Why is it positive? Because initially it is going to the right and right is positive. And then it will be going to the left in the second half, which will be negative. So it should look like this. It should go up, then it should come down, then it should come down, then it should come up. Okay, so this is the first cycle, and likewise you have to just repeat this one. So it will again go up, come down, keep moving down, and then eventually come up. So this is how, and this value will be negative V max over here. So that's how the situation should look like. It's basically a sine curve. It has to be a sine curve. All right, I think we do have one more part. A student sketches the free body diagram in figure 6 and makes the following claim. The free body diagram shows the force exerted on the block at t equal to 1.5. And they are asking that justify why this is not consistent with the graph of velocity as a function of time. Because the velocity as a function of time at 1.5 is giving me minus fx naught, minus v max, right? And as I can see that the slope of the velocity time curve gives the acceleration. And if I draw a tangent, slope of the tangent, I mean, gives the acceleration. And if I will draw a tangent at 1.5 t naught, which is right here, the slope is 0, which means that the acceleration is 0, which means that the f net towards the horizontal side should also be 0. But that's not what the student has shown. He has shown a net force towards the horizontal. So that is not consistent with the curve of velocity time that we drew earlier because of this reason.